All right, let's jump right into this explainer. We're tackling part 2 of our power quality discussion, and honestly, we're looking at the most debated grid side effect of AC variable speed drives on drilling rigs, harmonics. If you've been following along, you know that managing power quality is everything when you're running a massive offshore vessel, and understanding exactly how these drives interact with your grid is absolutely essential.
Just a really quick recap of our checklist to set the stage. We've already completely solved the reactive power issue. Modern AC VSDs inherently hold a high and constant power factor across all motor speeds. Check. We've also tamed that nasty inrush current because the drive gives us a nice controlled soft start instead of slamming the grid. Check. So that leaves us with the trickier challenge, the one with the question mark. Harmonics. It's the one that really gets engineers arguing, and it's exactly why upstream design decisions matter so much. So what's actually happening here? Well, a standard diode rectifier doesn't just draw a nice, perfectly smooth, clean sine wave from the ship's grid. Nope, it draws current in abrupt, non-sinusoidal pulses. And when you mathematically break down that pulsed waveform, you find these extra harmonic frequencies, specifically things like the 5th, 7th, 11th, and 13th orders, just stacked right on top of your fundamental 50 or 60 hertz grid frequency. These extra frequencies essentially circulate backward through the ship's electrical network, and if left unchecked, they cause unwanted extra heating and some serious interference with sensitive equipment.
Now, before we get into how we actually filter all this out, let's test your intuition a bit to see how this distortion actually behaves under a heavy load. Quick question for you. If you double the line current a drive draws from the grid to push a heavier load, what happens to its harmonic distortion? Take a second to think about it. Does it spike exponentially? Does it stay completely flat?
Well, here's the crucial takeaway. Harmonic current is directly proportional to line current. If you double the current, the harmonic distortion predictably doubles right along with it. They scale up together. A bigger drive pulling more current simply generates proportionally more distortion. And why is this such a big deal for marine engineers? Because it's entirely predictable. It's a direct, linear relationship, not some wild, rogue variable that scales unpredictably when operations get heavy. That predictability is exactly what lets engineers design filtration systems with total confidence. Moving right along to our next section, reducing harmonics through pulse counts.
First off, it's really worth noting that AC VSDs inherently reduce network harmonics compared to those older thyristor-based DC drive systems. But beyond that, it comes down to pulse counts and liquid-immersed transformers. Looking across these technological eras, a standard setup uses a 2-winding transformer feeding a 6-pulse rectifier. It works, but it gives you the roughest waveform. Step up to a 3-winding transformer, and those 2 secondaries are actually phase-shifted from each other, feeding a 12-pulse rectifier. That phase shift mathematically cancels out several harmonic orders entirely. And for the absolute cleanest current draw, you specify a 5-winding transformer feeding a 24-pulse rectifier. More phase-shifted secondaries literally mean more harmonic orders are permanently canceled before they ever even have the chance to reach the ship's switchboard.
Next up, let's look at topology, specifically contrasting single-drive versus multi-drive filtering.
When we compare these two main architectural choices, you're generally looking at either a single-drive or a multi-drive layout. In a single-drive setup, every individual motor has its own fully independent converter pulling directly from the switchboard. And because each one has its own independent rectifier drawing that pulsed current, harmonic filters are pretty much mandatory on every single unit. It's unit-by-unit filtration, which, as you can imagine, takes up a massive amount of physical space. But a multi-drive system, that's where it gets elegant. It uses one massive common rectifier to feed a shared DC bus, so you're filtering that distortion just once, centrally, right at the source.
And looking at the setup, because we have that central common supply unit feeding the shared DC bus, you'll notice there are no individual harmonic filters hanging off every single motor drive like your mud pumps or your top drive. You filter it once at the common rectifier, and it's effectively eliminated for every inverter downstream on that shared bus. Plus, this shared DC bus lets you do some really incredible things, like motor-to-motor braking. You can use one combined braking resistor bank for the entire network instead of sizing heavy individual resistors for every single motor. It is incredibly efficient. So let's quickly tally up the massive advantages of the multi-drive topology. By centralizing that filtration and sharing a common supply, you need far fewer breaker feeders in your switchgear. That translates directly into physical space saved in those super tight electrical rooms, a really significant reduction in overall rig weight, and a much lower total switchgear cost. It essentially turns the whole complex headache of harmonics into a predictable, streamlined engineering solution. You design it centrally, you build it once, and you can absolutely trust it.
All right, so we've officially mastered grid-side performance. We know exactly how AC VSDs handle power factor, tame those inrush spikes, and now manage harmonic distortion. But remember, grid-side performance is only half the picture. The other half is what the drive actually does for the mechanical application itself. Think about a drawworks suspending an incredibly heavy drill string. Can this AC system actually hold full, massive torque at absolute zero speed without burning out? That is the ultimate test, and we'll be tackling that exact scenario next. But until then, I'll leave you with this to chew on. If simply optimizing your electrical topology from single to multi-drive can save millions in weight, space, and switchgear costs, what other massive inefficiencies are just hiding in plain sight in your rig's design?